All right, this video is going to be on using transforms to solve differential equations. So it's going to focus on four main transforms. There's going to be the Laplace transform, Fourier sine, Fourier cosine, and exponential Fourier. And they look terrible, but I promise it's not that bad. So let's start with a problem, and we'll develop a process as we walk through the problem. Once we have the process, approaching any of these problems is pretty simple. Okay, so problem one. Let's say we have du dx squared plus dy squared equals 0. So let's say we've got that. We've got d squared u dx squared plus d squared u dy squared equals 0. And we've got a couple of boundary conditions. So we've got du dy x comma y equals 0 equals 0. We've got u at equals 0 comma y equals a function of y. And we've got the limit as x, it would be as y goes to infinity of u should go to 0. Yeah, the limit as y goes to infinity, u should go to 0. I don't even have to, yeah, sure, I'll leave it like that. Okay, cool. Step one is pick which variable we are transforming. So you always want to pick the variable that the homogeneous, the non-homogeneous boundary condition is a function of. So this is the non-homogeneous boundary condition, and it's a function of y. So we want to transform y. No. Process. So in this case, we want to transform y. I'm going to write it up here. Transform y. Oh, we also know one other thing. We know the range of x and y is 0 to infinity. Nope. What's a symbol for it? That's not it, is it? Oh, 0 is less than x, less than infinity, less than y, less than infinity. Okay, step one. We said we're going to transform y. Cool. Step two is we have to look at the range. And if the range is negative infinity to infinity, then we use exponential Fourier. That's a symbol for exponential Fourier. The X. The weird X with the little curly part on the end. All right, so if the range is negative infinity to infinity, we use that. In our case, y has a range, well, it should be 0 to infinity. 0 to infinity, so we can't do that. The other side, luckily, is 0 to infinity. So we're going to be up here somewhere. Now, this breaks apart. If we have an odd let me write that better. If we're transforming an odd derivative, then we use Laplace. If we're transforming an then that breaks apart again. But the reason for this is because Fourier sine and Fourier cosine, their odd derivatives they have a Fourier cosine in the Fourier sine, and they have a Fourier sine in the Fourier cosine. So if you're transforming odd derivatives, transforming it won't help because you're gonna be left with the Fourier sine and the Fourier cosine just sitting in there. So if it's a odd derivative, you use Laplace. If it's even derivative, then if the, what's it called? If you have a derivative of a function equal to 0, if that boundary condition is homogeneous, then you use Fourier sine. But if the derivative of 0 is homogeneous, then you use cosine. So that is the process. Took me a while to math this out, but I did, and it works like every time. Okay, so all right, we said we're transforming y. We're going to be up here because our range is 0 to infinity. Cool. Are we transforming even or odd derivatives? Here, y is an even derivative. So we're up here. Now, if f of 0 is homogeneous, then we use sine. If f prime of 0 is homogeneous, then we use cosine. For our boundary condition, we have effectively a f prime of 0 is equal to 0, which is homogeneous. So we have the f prime condition. So we have this one. So we are going to use Fourier cosine. Okay. So let's transform that term, since that is the term that we're going to use. Fourier cosine on y of d squared u dy squared equals should be that. And I think it is. Let's go. I'm gonna call it transformed u, because this is normal u. This is the transformed u. Normal u is a function of x and y. Transformed u is a function of x and lambda. Cool. So that is this term transformed. Now we can apply one of our boundary conditions. And this is why I mapped it out like this, because you can literally apply a boundary condition right away. We have this boundary condition. This equals 0. So this equals 0 because of boundary condition. Cool. And then we have this second term. I want to move that over. We don't split it apart like we did here. Instead, we literally just say it's a second derivative. Is that right? That is right. Cool beans. Cool beans. I am on a roll. All right, now we can plug them back into this equation. So we're left with cool. And now pretty much the rest of the problem is very easy. The rest of the problem for all of these types of problems is very easy. The hardest part is picking the right transform, and that's literally it. Picking the right transform is the hardest part, and I broke it down in probably less than 10 minutes. So what do you do from here? Well, you do the normal thing. You assume e to the kx. You plug it in, and you get k squared is that right? Yep. So then you get k equals plus minus lambda. Okay. Now, I've mentioned before that if you have, well, yeah, I mentioned before if you have a plus minus something, you can say that your solution is in the form, I think it's hyperbolic cosine. Let me check. Yeah, it's hyperbolic. I think that still works here, but because this is one of our boundary conditions, it's easier if we don't write it that way. But first, I forgot to do something. I forgot to transform the boundary conditions, which is very easy, but I just forgot to do it. So this transforms into d. What would it transform into? Yeah. And I think this should also be lambda. this will transform into so it's a different function, it's a transformed function. So you capitalize it technically. This will be as lambda goes to infinity, u goes to 0. Cool. Those are transformed. So we took care of this one right here. Now let's get back to this. So we said that's what we assumed. So we can say that u cool. Now we can plug in this boundary condition. Limit as lambda goes to infinity, u equals 0. So we have a, e to the infinity plus b, e negative infinity. And it should go to 0. And right now, this term goes to infinity. This term goes to 0. Let me write this over here. Goes to 0, right? Yeah. So a has to be 0. Because this already satisfies it. This doesn't satisfy it. So we just have to set a equal to 0. So now we've got u x lambda equals b e negative lambda x. Cool. Now I plug in our next boundary condition. Now I plug in this. I think that's literally it. Is that right? Yeah, that is literally it. So our final form, these are all hats, by the way. Yeah, okay. Cool. That's our final form. Now, all we have to do is untransform it. And we used Fourier cosine. So the untransform for Fourier cosine is this integral. We would be untransforming it with y. I think that's it. And this is where you stop. You don't go any farther than that. Because you could use MATLAB or whatever to do that integral. That's literally it. That's all the work you have to do. And the hardest part is picking the right transform. So let's do another one. Is this a good one? This one's a little boring. What about this one? Well, they're all kind of boring after you know how to do them, actually, so we might as well just do this one. Okay. Problem 2. All right, this c is just a constant, like a number or something. It's not a transform. So we have second derivative with respect to t, and fourth derivative with respect to x. And our ranges are those are our ranges, and these are very standard ranges, actually, because when you're integrating over time, you always start time at 0. Yeah, that makes sense. Okay, so our boundary conditions are our non-homogeneous boundary condition that we're going to use. That's another one that we're going to use. Help pick. I think that's it. Yeah, that's it. Okay. Before we add a third one, here we don't. You'll see why in a second. The third one, the one that we're missing is this one, but you'll see why in a second. Okay, so which variable are we going to transform? Well, what does our thing say? Transform the variable that the non-homogeneous boundary condition is a function of. Non-homogeneous boundary condition is a function of x, so we're going to transform x. Cool. Step 2. Range. Negative infinity or 0 to infinity. I think ours, if we're transforming x, x has a range of negative infinity to infinity. So we're going to use x, which, what's that one called? Exponential Fourier. And that's literally it. We just end right there. Cool. Fourier on x of, let's do this one first. Equals, that should just equal, yeah. Because that's not the variable that's being transformed, it's the other one. So here we go. I think we can pull the c out. Yeah, we don't even have to include it in here. We're just going to transform that part. Okay. Here we go. we're going to use this equation. So we have the fourth derivative. So we're going to have to the power of 4, which means we're going to have 2i squareds and lambda to the 4. And 2i squared is -1, 2i squareds is just +1. So we're just going to have a lambda to the 4th times the transformed function, I think. Is that it? That is literally it. Let's go. Okay, and like I mentioned before, we're missing this boundary condition because over here, we needed it to cancel out that part. But over here, all we have is that. So all we have is this part. We don't even have the second part that needs to be canceled out. Okay, cool. So now let's plug this stuff in. All right, kind of want to skip forward because we do the normal stuff. We assume e to the kt. We got k equals, I'm skipping steps here, but I don't really care, plus minus c lambda squared. What are our boundary conditions? Got to transform boundary conditions. In this case, what did I do? Yeah, I did it the not nice way. I left it, well, I mentioned before, you can write this either as like a cosine hyperbolic plus b sine hyperbolic, or just a c lambda squared t plus b negative c lambda squared t. You can write it either one of those two ways. Since we have this boundary condition, where we set it equal to 0, I'm going to say we should go with this way. Alternatively, if we had the limit, like we did over here, I would say we should go that way. But okay. So we end up with u There you go. Now we got to take the derivative. we plug in the boundary condition. K equals 0. So we're going to get, skipping steps here, but if we plug in 0, we're going to get that 0. That's 1. So BSD equals 0. And then I'm going to skip steps as well, but I don't really care. Plug in that. 0 equals F. So it's 0. Oof, maybe you do have to solve it the other way. No, you're fine. You're fine, you can do it this way. Okay. Plug in the second one, and you get U. Yeah, so that's literally it, right? Yeah, okay. So our final thing is that's our final thing. And then to untransform it, we have to integrate it like this. One over 2 pi Yep. That's the solution. Like, it's really not that bad. The hardest part is picking the transform. All right, should we do this one? All right, I guess we can start it. I don't really want to finish it, but we can start it. We can just say which transform we're picking. Cool. Beta, C, all of those are just constants. Our ranges are standard ranges, so negative infinity. They're standard because x can typically range from whatever, and when you're integrating with time, again, you start at 0 with an initial condition. 0 is less than t less than infinity. Our boundary conditions are u. You know what? I don't want to do this one because it's transformed. We also transform it with exponential Fourier. So same as the last one. Let me find a Laplace one. Here we go. I'm like, this one's going to be too easy. Like, this whole thing is so easy once you freaking make this process diagram. It's all super easy. Okay. Okay. Cool. So step one. Yeah, okay. So we're transforming t. Transform t. Step two. Take the range. T is greater than 0. So we're up here. Transform even derivative or odd derivative. T is an odd derivative. So what do we do? We use Laplace. Cool. Let's see what it says. For Laplace, they use S instead of lambda. It doesn't matter though. You could use whatever you want. Maybe I should have just written lambda, or maybe there's a reason behind it and they never taught it. But okay, so we're using that transform. I'm gonna copy that over here actually. Just put it right there. I'll erase it afterwards. Yes. Is that right? Yes. Cool, and with that boundary condition, we can cancel that out. And then the other one, cool. Then what do we do? Yeah, then it's in normal stuff. We make our equation. I skipped some math there, but that's fine. You could do hyperbolic sine or hyperbolic cosine, but since we have limits, e is leaving it in e to the power of is easier. Limit of that one. So this one, what would that be? Plug in infinity, it should go to 0. If you plug in infinity to this, it goes to infinity. If you plug in infinity to this, it goes to 0. So we have to say a equals 0 because of the boundary condition. I think this one will satisfy as well. We don't even have to change anything. Let's just double check. Yeah, if we plug in that into here, this will just go to 0 anyways, so we don't even have to set b to anything. Cool. So this boundary condition is met. It's basically useless. All right, what do we have next? Then we plug in this. X equals 0 equals that function. So x equals 0, this whole thing goes to 1. I'm skipping a lot of steps here. This is not how I would write it if I'm doing it for the first time. But we get negative b root s equals transformed g of s. Because when we transform it, this goes to g of s. I'm skipping so many steps for this problem. When you're solving it, solve it how I did here, where I wrote out every single step. Yeah, that's literally it. When we get u e, which is negative g s over root s e negative root s x. Yep, and then how do we untransform that? This. I don't think we ever learned what c minus I infinity, like I don't really know how to do that. I mean, I could just plug it in and see, hopefully everything works out. I'm not even gonna worry about it. I'm just gonna write it out. I'm gonna copy it over though. That's literally it. So that is how you pick which transform you're using to solve a differential equation and what each transform is. And here's a couple example problems also. And they're really not that bad. Cool.